I wanted to start off our discussion of how muscles work by giving a little bit of a historical perspective and starting from maybe how people used to think muscles worked, or what people's initial ideas about how muscles worked were, and then start to show how our understanding of the actual function of muscles has evolved over time. So we have an intuitive understanding of what muscles do. So I have a little sketch of the bicep right here. We understand that the bicep muscles create a force like this that tends to pull the arm up like this, which acts or overcomes the force of gravity that's pulling down on the barbell or the dumbbell like this, correct? Now, I think, have this unexamined intuition that muscles contract, kind of going from being almost deflated like a balloon to being inflated like this. And that intuition is actually powerful enough that in the 1950s, people started making mechanical models of muscles that worked essentially like this. You have a balloon inside of a sleeve, and then you pump air into it, and the balloon inflates. And as it does so, the sleeve contracts and creates a force like this. Now, if you were a scientist, you might think about doing an experiment to determine how much a muscle puffs up like this when it contracts. And so, thinking about the famous story of Archimedes, you could maybe think up a clever experiment where you get a big bucket, a big like Rubbermaid tub or something, and you fill it with water. So fill it with water, and you're going to dunk your arm into that bucket, and you're going to relax your muscles completely. Okay? So, according to our current hypothesis about how muscles work, your muscle should be kind of deflated like the balloon down here, and then you could record how high is the water. Because if your muscle puffed up during contraction, the increase in size or the increase in volume would displace some water, and the water level would go up. This is just like Archimedes in the bathtub. So by measuring how much the level of the water went up, calculating this volume of water, you'd know how much the muscle inflated. Now, there's something very interesting that happens when you actually do this experiment, which is that the change in the volume of the water is 0. So, in other words, the muscle doesn't change volume when it contracts at all. Just to clarify what I mean here is, if your muscle's relaxed, the water level is here, and then you flex your muscles, you flex your bicep as hard as you can, and the level of the water doesn't change at all, which must mean that unlike this intuition we've built up and this maybe engineering model of how muscles work, that is not how muscles work in the body, because they clearly do not change their volume. So this was very puzzling. This was something that people knew in the 1700s, 1800s, but it was not until about the 1920s or so when advances in things like biology and specifically having electricity available to start doing experiments on animal muscles, especially frog muscles, started giving some understanding of how muscles behaved. So during the 1920s, there was a fellow named A.V. Hill, who, if you've done exercise physiology, was also very involved in understanding how oxygen is consumed by the body to produce energy. But A.V. Hill did some experiments, and he was able to show that there's some very important and characteristic properties of muscle. So what did he find out? First of all, the force of a muscle is proportional to its cross-sectional area. And this is pretty intuitive, but a muscle, say one muscle like this, another muscle like this, the cross-sectional area, same idea, by the way, that we were thinking about when we thought about dividing force by cross-sectional area to get mechanical strain, or to get mechanical stress. The force that a muscle produces is proportional to its cross-sectional area, meaning this area right here. So if the muscle gets twice as big, then the force goes up by a factor of 2. And number 2, and we'll go into much more detail on why this is, but muscles produce much less force when they're very short or long. And let's say when they are shortened or lengthened beyond their normal length. So if a muscle is too stretched out or too shortened, and how that would happen, of course, is, say we're considering the action of the soleus muscle here. Notice how plantar flexing and dorsiflexing the ankle like this would shorten or lengthen the soleus muscle. That changes the force in the muscle here. So maybe we could say forces depends on muscle length. Let's say that. And number 3, muscle's force also depends on its velocity, meaning how fast it's moving. And how A.V. Hill arrived at these conclusions was with many different iterations of an experiment like this. Suppose you get a little container and you fill it with some saline or some other something that'll keep a muscle from, say, a frog, in quotes, alive, meaning not drying out or deteriorating. And then take a frog and get one of its muscles and attach it to something here. So we've got a frog leg muscle like this in our solution to prevent it from drying out. And we're actually going to do an experiment really similar to what we envision doing to test the mechanical properties of tendons and cartilage. So we'll attach it to our force gauge like this. As I mentioned maybe a week ago, this is quite analogous to the gauge you use when you're fishing to tell how heavy a fish is, because it just measures. In that case, you're measuring the force of gravity acting on the mass of the fish, but you can use exactly the same kind of device to just measure what the force is. And you just zap this muscle with electricity to make it contract. Connect it to a little battery or something. And you test it at a bunch of different muscle lengths and a bunch of different velocities. And you would induce a velocity by maybe starting to pull on it and setting the length at a particular length. And we'll go into much, much more detail on what those properties actually are. But the really impressive thing about this early research in muscle physiology is that A.V. Hill and related researchers knew almost nothing about the microscopic structure of muscle because they just didn't have the tools to understand what muscle was doing. So the only things they knew were that bigger muscles make more force. The force of the muscle depends on the length of the muscle, and the force that a muscle produces depends also on the velocity it's moving at. Finally, they knew that muscles do not change their volume when they contract. So this was the starting point for a lot of the models that we use to think about muscles, and those models are so good that they, in fact, continue to be used this day. And in the next few videos, we'll go in more detail on exactly where these ideas come from and what kind of implications they have.